Can you hear me now? Thanks for the tip. Being our first time, I'm just gonna wait maybe 5 minutes for people to come in before I just jump ahead and get started. Okay, great. I'm glad some people are coming in. Oh, great. Well, I haven't been talking, so that's okay, Zoe. So thank you for tuning in for our lecture. This is the very first time I'm doing something like this, so if it's a little rough and not polished, please bear with me here. The other thing is there is a 30-second delay from what I do to what you see, so please feel free throughout the lecture to interrupt me with questions and clarification as always. But it'll take me at least 30 seconds to get back to you. So I'm not ignoring you. It's just the nature of how this whole thing works. So today we're going to get into Ampere's law, which kind of covers off the rest of the stuff we'll be needing for the midterm. And Ampere's law really, as you've seen from the pre-lectures, is really much very similar to Gauss's law in the sense that yes, last week we were able to do a bunch of integration using the Biot-Savart law to get all kinds of current wire shape and do all kinds of hard work to find out the magnetic field of a bunch of different arrangements. But, you know, some of the integration got a little bit heady and the direction kind of makes your head explode. So people wonder if there was another way to appeal to more of the general magnetic field diagram distribution, much like how Gauss's law kind of worked. So with Gauss's law, right, the idea was to, going back to the electric field, right, we had some positive point charge that goes, have electric field that points outwards from, say, a positive point charge everywhere. And then we kind of realized that the Coulomb's law gave us this kind of expression, R square epsilon naught. And so people notice, oh, if we draw like a sphere around here, we can kind of relate the direction of the field lines, a bunch of field lines going out, to the point charges that are caught inside, in this case positive. And so we drew Gauss's law based on that, right? Look at the electric flux, which is defined to be this mathematically, and that's going to relate to our Q enclosed related by the constant epsilon naught. So what if we were to apply the same thing for magnetic field? Well, the catch with magnetic field is always created in these loops, right? There's no kind of beginning or end to these So if we were to say draw a Gaussian surface, say here, you'll notice that all the fields coming in will equal all the fields going out. Same thing if I draw here, here, it doesn't really matter, right? They all go in the loop. So for a loop of current, that's true. For a solenoid, that's still true, right? If I draw a Gaussian surface, say here, I have a bunch of fields coming in and a bunch of fields going out. So a Gaussian surface, even just inside, all the in equals the out, right? And that is actually also true for a permanent magnet. So inside permanent magnet, we actually draw the magnetic field line through as well because it's a dipole. So they also come in loops, and therefore they also give you no net flux. This is, of course, also true for a straight wire, right? These are all in circles, as you can see, and so all the in equals the out. So this brings us to what if we try to apply Gauss's law to magnetic field? Well, if you apply Gauss's law and draw a Gaussian surface to find the net flux, in this case net magnetic flux, which can be defined as B dot dA and closed surface integral, that's always going to give you 0. This is just basically an statement of the fact that we never ever find just a single north pole sitting around somewhere. North and south poles, they're always coming in pairs. So we don't have the situation where, say for electric field, we can have a point where all these different fields terminate, and then we draw the Gaussian surface, we get a negative net flux. That doesn't ever happen for magnetic field. So that's why when you add up the net flux, net magnetic flux around any Gaussian surface, you always get 0. So while that is very fascinating and it's a deep revealing truth about some fundamental fabric of the universe, it's not actually immediately useful for us to try and find the magnetic field for a specific point. So a different approach is required, and that's where Ampere's law comes in. If you compare the forms, once again, of Coulomb's law, right, it's got this very critical 4 pi r squared, which is the surface area of a sphere. Right, and that's the hint to tell us that, oh, we can relate something about what happens through the with the magnetic field, with the electric field on this spherical surface with the volume that's enclosed inside. While you might argue that we have a similar thing with the Biot-Savart law, right, it's also got the 4 pi r squared. The thing that's actually more useful is if we consider the magnetic field of a straight wire. So in this case, if we have a wire coming straight out of the page, by the right-hand rule, we know that the magnetic field is going to go in a circular fashion around that wire, and the magnitude of which we worked out through integration was and then the hint here is that, as I alluded to last time when I discussed it, this 2 pi r here is the circumference, or the length, I guess, around a circle. So then once you have a circle, let's draw the circle right on here. Circle, right? Then you're looking to relate it with an enclosed area instead. And with area, then we can talk about the current that goes through such an area. And that's kind of the basis of how we approach coming up with Gauss's law. Sorry, Ampere's law. I'll get that confused all the time. But so what Ampere law states is that if we draw some random loop in space, right? In this case, if we think about it as a circle for now, we have this loop in space, and then we take this funny integral around it. Actually, let's draw in the wire again with a more different color this time. The magnetic field goes through like that. So what Gauss's law, what Ampere law is trying to say is if we add up all the magnetic field as we go around this loop, then we can say some statement about the current that's enclosed within that loop, or specifically the current that goes through the area that's enclosed within that loop. So that's why we do this dot product to say the amount of magnetic field that goes along my loop. So in this case, dl, say goes like that. And then we took the dot product because the magnetic field is perfectly tangential. Everything works out. And then we're going around this loop, right? No longer a closed surface, but a closed loop because it's dl and not dA. That's going to be related to the amount of current that's enclosed, related by this constant mu naught. And that's where mu naught comes from. So that's why in the Biot-Savart law we use mu naught divided by 4 pi. That's where mu naught comes from. It's defined in Ampere's law. Now this thing here, we don't give it any special, we don't give it a name that we use very often. We just call it the loop integral. Unlike flux, we don't give it a special name. It's just the loop integral. In applying Ampere's law, however, we do have to introduce yet another right-hand rule. Because in order for the signs to be consistent on both sides of Ampere's law, you notice if we have a choice, right? As we go around the loop, in this case, we can go around the loop counterclockwise or clockwise. So if we're to go through the loop clockwise, your B, your magnetic field, and your dl in this case, as we go around the loop, it's in the same direction. So then B dot dl would be positive. Right? So then that must correspond to a positive current. So that's why your integration direction is related to the direction of the positive current, right? They have to correspond to one another. So in this case, if we're going through the loop clockwise, if we're going through the loop counterclockwise, then the current that's coming out of the page, we expect to call that positive. By contrast, if we have the same situation, right, but we decide to take my loop, Actually, let's draw in the magnetic field first. The magnetic field is still going to go that way. But if we choose to take our loop clockwise in this case, what you'll have is you'll have dl going that way and b going that way. So then, in this case, b dot dl would be negative because they're in opposite direction. Which would correspond to the fact that, which we have then redefined because we're taking the loop in opposite direction, we have defined the current now coming out of the page to be negative, to be consistent, right? So that's why the two are related. And that's where the right-hand rule comes in. So again, we're going to draw this. It's another one of these thumbs up one, where if this is your integration direction, then this would be the direction of positive current. This one is a little bit more abstract in the sense that both of these things are kind of fictitious, right? It's for us to define a coordinate system. It doesn't correspond to the actual direction of the current. It's just that if the current happens to go the other way, we call it a negative current. If we go in the way we have defined here with the thumb, that we call it a positive current. That is all. And then with the same integration direction, right, we decide which way to go. And if the magnetic field happens to be in the same direction, then the dot product is positive. And the magnetic field is in the opposite direction, then the dot product becomes negative. So these are just things to help us do Ampere's law. They don't directly deal with the direction of the current or the direction of the magnetic field. It's just what we call positive. Yep. So yet another right-hand rule for you. The one more note here with Ampere's law is that the current doesn't actually directly have to go through perpendicularly. We just count all the currents as long as it goes through one way or the other. So if you have the Amperian loop, let's look at the loop sideways, right? There's the loop, right? So the loop kind of goes swirl like that, but we're looking at edge on, right? Then if we are going to integrate, let's say we integrate out this way and in that way, right? So if we go through with our hand, we expect this direction to be where positive current is positive in that direction. So in that case, this is clearly a positive current. And if current goes that way, that's going to be called a negative current. But these also apply. So as long as you're going from, I guess in this case, the left to the right, we'll call it positive current. And this is still positive current because it's going to the left to the right. Even with the angle, it doesn't matter. That's kind of what the point I'm trying to get across. The current doesn't actually directly have to be perpendicular all the time. So let's go through a couple cases then. With Ampere's law, of course, you'll get a bunch of... Let's write Ampere's law again. So with Ampere's law, you'll probably get some number of questions that very similar to your Gauss's law question, where the geometry is really ugly and that we are just asking for the entire integral without you having to find out the magnetic field at a specific point. And those are easy because if we're asking for this whole thing, all you care about is what is the current enclosed. Of course, with Ampere's law, you have to worry a little bit more about the direction of the current, what counts as positive, what counts as negative, etc., etc. But there is a few cases with really high symmetry where the loop integral evaluates nicely and we can actually get some results for magnetic fields. And as you suspect, similar to Gauss's law, it's very limited to a few cases of very, very high symmetry. So we'll visit those cases. The first one is for an infinitely long wire, right? That's the case of the cylindrical symmetry. And before we apply Ampere's law, we already have to basically know the direction of the magnetic field pretty much everywhere. That's just the nature of it. It's very similar to how when we did Gauss's law. So using the right-hand rule, right, we know that if the current goes from the left to the right, we know the way the magnetic field swirls around that wire, and it's consistent with the picture that is drawn. So if we were to then draw it head on, then we can then use Ampere's law to find out the magnetic field at a specific point that is a distance r away from the center, right? If we're interested in this particular magnetic field. To do so, we have to draw a Ampere or Amperian loop, that's a fancy word for it. We'll draw a loop that includes this point, right? But that it's drawn in such a way that at every single point, we expect the magnitude of the magnetic field to be the same. And by the cylindrical symmetry, the way to do that is to draw a circle around such that every single point, the magnetic field is expected to be tangent to the circle, and that they should have the same magnitude. And these are things very similar to what we've written for Gauss's law, right? Where by symmetry, we expect your B to be parallel to your DL in this case, and that your B magnitude is the same at all points on the loop. This is what we need then to simplify my loop integral to actually get me something useful. Right, we'll deal with this side first, right? We talked about how B dot dl, they're parallel, so that's just equal to B dl, magnitude-wise. And that this is uniform, right? Same everywhere, so it comes out of the integral, and we're left with the magnitude of B and the loop integral of just dl, right? Which would be just the length of the loop, which is 2 pi times little r. And then with the I enclosed on here, the only current that's inside this loop coming across through the surface is this current coming out of the page. And by the right-hand rule, since we're integrating, in this case in the counterclockwise direction, the positive current is the current that's going to be out of the page, so we call this plus I. And that's how we use the right-hand rule with Ampere's law. So then this becomes the magnitude times 2 pi r. It's equal to mu naught times I. So then your magnitude of the magnetic field is mu naught I divided by 2 pi r, right? Consistent with what we were getting before through integration. Arguably a little bit faster. And this works for any given r, right? If the r was bigger out here, then you would draw a bigger circle, right? And so everything corresponds. This again only gives us the magnitude because we already need to assume certain things about the direction of the magnetic field already. So this just gives us the magnitude, and then you can fill in the direction information yourself. So that's all nice and good, right? We now have Ampere's law giving us the same result as the other method that we did. But Ampere's law allows us to solve certain problems and get certain insight that is a little more difficult to get the other way. And specifically, it's the case of when you have to talk about what happens inside the wire, right? We're not looking at the wire as just a single point anymore, right? If we consider the wire to have a big extent, and we have to assume then this is... Actually, we don't have to assume because we went ahead and proved that once upon a time when we talk about current, that through a wire, the current should have a uniform current density. Current density being the current divided by the cross-sectional area of the wire. It's going to be uniform throughout the wire. So in the case if we're interested in the point, I guess we have to give this a direction. So let's say the current direction. So you can think of the current being, everywhere inside, right? I'm not going to draw them all. But the current is distributed inside the wire. Now we're interested in the point outside, right? And we want to find the magnetic field there. Then we do exactly what we did in the last slide, right? We draw a Gaussian surface, an Amperian loop that's that big, and then we find out what it is because it encloses all the current. But then the question is, what happens if we're inside here? So if we want to point inside, then we would do the Amperian loop that includes this point that is inside, right? Let's give this another variable. Let's call it big R, right? Distinguish that between big R is the radius of the wire, whereas the little r is the radius of my Amperian loop. So again, we're going to integrate in the counterclockwise direction, so my current should count as positive. Your I density is going to be divided by the entire area, so that's pi big R square. And so, writing Gauss's law, keep doing that. Writing Ampere's law, we write that. By the same argument, we still have that your B is going to be parallel to your DL, and then your magnitude of your B is the same. So we're going to end up with, again, B factoring out, and we're just taking the length of the loop, and the length of the loop is in this case is 2 pi little r, right? Not big R, right? Because it's just the size here. The current enclosed, because we're only taking part of the wire, we're not taking the whole wire, right? That's the current density multiplied by the area that's enclosed. So then that's just pi little r square. So then overall, that's like that with respect to the overall current. We're only taking a fraction of that wire. So a fraction of that current. Putting that all together, then we have B is equal to to that. So it doesn't have a 1 over r dependence, it has a linear dependence. Because as your loop grows bigger, your area increases by r squared. So that's kind of what Ampere's law kind of help us further our understanding of these distribution. Just with an alternate tool, we can do different things. Yes, this J here is for current density, yes. Then another case that we usually go through is the case of the infinitely long solenoid. Right? Important in the sense that, it gives us a straight magnetic field, but also, as we'll show now, a uniform magnetic field. Last week, we did a whole lot of hard work, right? We integrated the little current element into a loop, and then we integrated that into a bunch of loops to make our long solenoid, and then we set that to infinity to get the infinitely long solenoid case. But that only gets us just along the middle of this distribution, right? Just along the middle axis. So with Ampere's law, we can pretty quickly get to the same result, and also finally prove that the magnetic field inside an infinitely long solenoid is in fact uniform through the cross-section as well, not just through the length of it. So the first concept of applying Ampere's law is you have to kind of have some idea about the magnetic field direction, at least, right? So imagine if this was made really, really, really long. Imagine this was made very, very, very long, then the magnetic field would be very strong inside, right? But it wouldn't ever be allowed to escape and loop back around. What ends up happening, therefore, is all the magnetic field is expected to be straight across on the inside, because they can't curve, right? Because this thing is infinitely long. And then they're trapped inside. They can't loop back around, so everywhere outside, the magnetic field must be zero. So therefore, if we take this is a cross section then of the solenoid. So on the bottom you have all the magnetic field, all the current coming out of the page, looping back around to be into the page. And so in this case, because of the geometry of the magnetic field, we draw a rectangular Amperian loop instead. So we have to deal with each part separately. So let's deal with the Amperian loop first. In this case, I guess we're still going counterclockwise. This is clockwise. So because it's a clockwise thing, dl goes this way on here. So your B is once again parallel to my dl. And within here, again by symmetry, because we are at the same distance away from the center, right? That's the same r. We expect that the B again to be the same. So, okay, so let's take apart each part, right, as we go around the loop. Let's do the easy bit first, which is this bit. So everywhere outside, right, all this stuff, because B is equal to 0, then your integral of B dl must be equal to 0 at those points. These parts, you have non-zero B, that's true, but B is perpendicular to my dl in those cases, right? dl goes that way in those cases, so therefore your B dot dl being a dot product, evaluates to 0. So the only part that has that has this integral b dot dl is this chunk here. And within this chunk, you do have that and b same. So then this whole thing, right, becomes just along section 1. And then that comes out, so then along section 1, and then the length of this is just this L here. So that's L like that. For your current density, for the current enclosed, you're looking at all these wires inside. They're all positive, right, because they're into the page. For a right-hand rule, if we're integrating this way, then this is positive into the page, right? Your thumb goes into the page. And so, but we don't have just the one current, right? We're enclosing a number of wires based on how long my Amperian loop is, right? This length of the Amperian loop we draw arbitrarily. It doesn't matter how long we draw it. It has nothing to do with the length of the whole solenoid itself. That's infinite. So that's going to be some number times the current through each of the loop. So if we put it all back together, a little messy, sorry. B will be equal to mu naught N over L, right? So N enclosed, I guess. Number of wire enclosed. And this here, right, it's so many wires in so many length. That's my loop density, right? Little n. Exactly the same as the result we had found last week. Now the added insight here is that this whole derivation here, oh no. This whole derivation here, there was nothing specific about along which line we're drawing this section 1. We can draw section 1 down here, section 1 down here, section 1 down here. It would give us the exact same result. So this really proves that not only is the magnetic field the same all the way along the length of the solenoid, but it's also uniform across the area of the face of the solenoid. So with an infinitely long solenoid, in fact, we do have a uniform field everywhere inside. And this would have been a lot harder to prove with integration because it's off-axis, no symmetry, all your integral gets really, really ugly. So that's the solenoid case. It's more really for you to see how it all works and Ampere's law apply. I mean, the results is simple and you can of course make use of that. And then the last case is the toroid. Now, a toroid is really pretty much similar to a solenoid. It is a series of loops, but it's like we take the solenoid and we take the two ends and join them together. That's what a toroid is. In case you... Another way of visualizing it is thinking of... Let's see... Oh, wait, no, not that. A good visualization is this: a slinky toroid, where you take the two ends of the slinky and you wrap it around and join them against each other. So that's the shape of a toroid. Now down here, you can also see kind of like if you cut it open halfway, right? You kind of see the cross section of the slinky. So in this case, each loop makes a circle as well. But that's not necessarily true. I mean, you can still you can have each length to be like a square shape or triangular shape or a star shape, right? It will still work, right? But as you wrap it around, the outside overall thing still looks more or less like a circle. So the way to analyze it, no matter what the shape is, we can analyze it pretty much the same way. We're going to cut it straight across in the middle here to look at that cross section. So how does that look like? Looks like that. You have a bunch of wires inside. In this case, the current is coming out on the inside bit. And then it kind of goes in like that. Whoop, whoop, whoop. If you just draw the wires on top, it kind of looks like that. So as we draw, if we're interested in then the magnetic field of a point inside the toroid, where we expect there to be magnetic field, then we draw by the symmetry a Amperian loop that's also circular. And then because it's like a solenoid, we expect the magnetic field to kind of go tangent to the circle again, travel in this circular loop inside. Oh, the direction. If you're ever curious about the direction, you just pick one particular point of the current, say this one right here, and then you apply the right-hand rule. So I applied the right-hand rule coming out of the page, and so it loops around this way. So inside my loop here, I know that it goes this way like that, and it'll be consistent for every single point. You can try for this point as well. It's going to go that way. You can try for an outside point. They're all consistent, so you don't have to pick one particular current and then deal with the direction of the magnetic field. So once we have that, then we can now decide to draw a Amperian loop that is likewise a circle, right? That goes around like that. And we can arbitrarily decide to integrate counterclockwise. So here once again we have my B and my DL to be exactly parallel, so and again uniform because it's all the same distance away by symmetry. So this just becomes once again that simple expression, which is then 2 pi, I guess, R. Now the current enclosed, you notice all the current that's inside, we again ignore everything on the outside, right? Just like Gauss's law, while whatever's outside is important to make the magnetic field have the direction that it does, for the calculation, we ignore all the current that's outside of my Amperian loop. What's inside, though, is every single one of these wires, right? So it's the current of each wire multiplied by, in this case, the total number of wires. The total number of wires, the number of loops, right? This is no longer a loop density thing like we had with our solenoid. This is the total number. Everything every single one of these wires is inside my Gaussian my Amperian loop. So then we end up with a fairly simple expression of mu naught n I over 2 pi r. Which then, funny enough, if you notice, it looks very similar because this term in here, that's basically your loop density once again, right? That's your total number divided by your total length. It's pretty easy to get as a result. And it has the added benefit that none of the magnetic field escaped. And we'll see why that is useful. If not next week, the week after when we do inductors. But one thing I like to point out is that in this case, your B does have a dependence, an inverse dependence with R. So the B is not uniform within a toroid. As you go further out, right, as you on the outside edge, your loops are less dense, so your magnetic field is less strong. If you're on the inside edge, your loop is more dense, therefore your magnetic field is expected to be stronger. Of course, you can make a very skinny toroid like that so that it's roughly uniform because the difference of R between here and here might be slight. Not that we usually care too much about that, but in certain application, you can make that work. On the same token, we can also look at how do we know that there's no magnetic field outside, right? So if we're interested in a point here, right, then we would draw an Amperian loop like that. In this case, the current enclosed would be 0. There's nothing inside, nothing going through my surface, right? So therefore, your B would be 0, because then your loop integral is 0, and therefore it's 0. Do I have another one? Ah, yes. So then, if we're considering the case outside, right, this R here, similar argument. So if we want the magnetic field here, we would draw an Amperian loop that's that big. And in this case, it encloses all of the wires with the current going out and all the wires with the current going in, right? So your I enclosed in this case would be, now if we're going through the loop this way, using your right-hand rule, everything that is, so you have N times I positive because these are the outward going current, whereas all the inward going current is going the opposite direction as given by our right-hand rule, so that's going to be plus negative N I, right? These are all the ones going inside, which then when you add it up gives you a big fat 0. So then once again you can say, therefore my magnetic field outside for points outside bigger than my outer radius, it's also 0. So the toroid, more than the shape being, delicious looking, it has the added thing where all the magnetic fields inside and all the points outside should have no magnetic field, which would be useful if you don't want the magnetic field to be messing with other parts of your circuit. So that's the other key thing with the toroid. But the analysis should be very similar. And I'll leave it there. Capping off Ampere's law, there's a couple small limitation to Ampere's law. The first one is just like Gauss's law, right? The line integral here can get nasty and might not give you results if there's no symmetry, right? We already went through the cases of symmetry, so similar to Gauss's law, we're limited to those cases of symmetry. But on top of that, with Ampere's law, there's an added requirement that the current needs to be steady, meaning not changing in time. when the current does change in time, that's going to get us a completely different physical effects that comes into play, and we'll cover that towards the end of the term. So for the purpose of this midterm coming up, for sure, for this week and the midterm coming up, we're going to assume that whenever we have to apply Ampere's law, the current is in fact steady. It's just that be aware that there is that limitation. Now, if you allow me maybe 10 minutes or 15, want to cover another topic really quickly, and then we'll talk briefly about the midterm before we part ways. And that's to cover magnetism and matter. So remember, for electric field, right, we had these things called dielectric constant, where we can just replace epsilon naught with some kappa epsilon naught, and we can do our calculation the way we do things. So, and that applies when you expose electric field to some insulating material, some dielectric in that case. So what happens when you expose magnetic fields to matter? Because all this time we're dealing with mu naught, which is the permeability of free space, right, vacuum. But if we're in a solid, what happens? Well, something very similar. We also characterize it by some kappa magnetic, and we replace mu naught with kappa mu naught. Now, there's generally a few major cases that happens, and we classify material based on these few cases. But essentially, you can imagine that in most solid, right, each individual atom or particle or whatever has some amount of intrinsic magnetic dipole moment, right, as discussed in the video I show you, right? There's a little bit of magnetic dipole moment happening in each of these things, and when we expose it to some external magnetic field, some of them ends up being aligning, and then that adds. So this alignment adds to the external magnetic field. So unlike the case of the dielectric, where it creates an electric field that cancels out partially some of the electric field, your solid adds to the magnetic field by aligning itself. And this applies in most solid, actually, and we call those solid paramagnetic. That's the most general. That's probably one of the most common case, that each of the atoms have some magnetic dipole moment, but it's not very strong. So even with external magnetic field, they only align pretty weakly, right? And then it gets randomized again because there's thermal agitation or they're locked in the crystal lattice or whatever. And so the alignment is very, very weak. And we call these paramagnetic material. They are the material with, as we measure what happens to the magnetic field, so it adds only a little bit. So your kappa B would be greater than 1, right? Because you're making your field bigger. But not typically, they don't go very much more than 1. It's on the order of 0.0001 kind of thing. They're fairly small. Then we have another class of material called diamagnetic, where intrinsically the magnetic dipole moment is very small to begin with. So each atom have basically no magnetic dipole moment, so there's no possible alignment that happens. So the magnetic field doesn't even get strong at all. So you might think that the kappa B would be exactly 1, but due to this other effect called because this effect doesn't show up, and a further weaker effect called due to the Faraday law, to be covered next week, actually makes it slightly weaker. So In fact, in diamagnetic material, the kappa B is less than 1. Now, again, it's also pretty weak, so we're talking about 99991 or something like that. Very, very slight. Then probably the most interesting of the types, we have paramagnetic, diamagnetic, and of course we have ferromagnetic. And these are cases where atoms have very strong magnetic dipole moments that strongly aligns. In fact, it's so strong that once they become aligned, the magnetic field that they're generating maintains its alignment and therefore makes what we call permanent magnet, right? Permanent. Or what we think of as permanent magnetics. Once we align it with some external field, it stays aligned. And then the B is way, way stronger in these material. Super strong. And here we're talking about kappa being on the order, say for iron, it's about 5,500. So compared to most normal material being 1, your iron has a kappa of 5,500, which effectively means that if you shove an iron core inside a solenoid, right, you replace the mu naught with kappa mu naught, in this case K, you go from this number for magnetic field to basically 5,000 times of that. So that's why if you were to make an electromagnet, most electromagnet doesn't just have a coil sitting out in the air, it's got some kind of iron core inside that magnifies the effect. Not only does it magnify the effect, also has the added effect of channeling the magnetic field. So you can shape the magnetic field by channeling them through these material. One example, really quickly, is I showed you the hard drive last time, right? One of these hard drives here, you can have a coil out here generating the magnetic field, and that magnetic field gets channeled along the metal, only to escape briefly wherever you want it to escape. So if you were to make a write head on a hard drive, you make it like this so that it all gets channeled through here and just jump across here very intensely. Cool. So that caps off all the material we're covering for the midterm. The midterm itself is, I already shown you through email what to expect. I'll email that out on Wednesday, and then you do it. Then you submit it on D2L. I'll make a submission folder just like your muddiest point. And the things that are covered is starting from electrical potential. I know it's a long time ago. Look back at those stuff. Know how electrical potential relates to electric field, how to integrate it, how to find it out at every single point, etc., etc. Then we had the simple circuit stuff, capacitor. Then we had magnetic force, which is what we did 2 weeks ago, and creating magnetic field either by Biot-Savart law, integration, or what we covered today, finding out by Ampere's law. So that's all the material. And just to cap off really quickly, I know I'm kind of running a little long today, is to kind of go through all the different right-hand rules that we did, because a number of you in your muddiest point mentioned that that was an issue for many of you. And in fact, we do have many, many right-hand rules. It's not just the one, right? To help me organize, I usually think of I have a whole bunch of right-hand rules associated with dot products. So in fact, there's only one right-hand rule there. For all, not dot product, cross product. For all cross products, I use the one of the 3 fingers, right? A cross B gets me C. So by looking at the form of the equation I have, I know that this is my thumb, that's my index finger, that's my middle finger. That's my thumb, index finger, middle finger, right? So that's all consistent. As long as you know the order of the dot product you're dealing with, then you can just use the three-finger way. Yes, in fact, I think it just gets saved automatically. So you can even right now rewind to wherever you want, and it will just be there forever. I think that's how YouTube works. The midterm will in fact be open book. You can have all kinds of material access to you. Although in the sake of time, I still recommend you to write up 1 or 2 reference sheets just so that you have everything in front of you. You can get really quickly and just get going on the actual questions. Don't spend all your time looking up specific formulas or, oh, I remember that particular example is exactly like. No, just know the stuff and do it, right? That's going to be faster for you. Then, aside from the cross product ones, or the cross product 1, we have a whole variety, a whole slew of things that relates something that goes in the circle and something that goes in a line. So, in this case, if you have omega, if you remember back last term, you can torque. I guess this term we talk about torque with the motor. If you have a torque vector pointing out of the page like that, then your right-hand rule tells you the midterm is going to be next Wednesday, same as what it was originally scheduled. So for you guys, I'll send the email out with the midterm over email around 8:30 or so. So if you don't get anything by 8:40, make sure to email me and I'll see what happens. So back to this, if the torque vector is pointing out of the page, that means it's pushing things to go rotate in the counterclockwise direction. So the format of the midterm is expected to look exactly like midterm 1. 5 multiple choice and 8 other questions. So exactly the same format as all the old midterm I posted up. I didn't want to really change things up too much. Then we talked about the magnetic dipole moment. So this is relating the current in a loop of a current carrying loop, and then your thumb points towards the direction of the magnetic dipole moment that we define. So then we went to the magnetic field caused by a current. So the current is coming out of the page, and the magnetic field we know swirls around in the counterclockwise direction as well. And then today we introduced the fact that if we have a Amperian loop that we draw in space randomly, and your DL points that way with the fingers, then this would be the direction of positive current. So that's kind of a summary of all the right-hand rules that we covered. So hopefully that cleared things up just a little bit. And I guess I'll stick around here for question for maybe another 5 more minutes. And if you have further questions, please feel free to email me at any time. Thank you. Oh, also, if you have any feedback about how this whole thing went, I would love to hear some. Thanks. The J part. So that's with regarding the current inside the wire. So maybe I can redraw this a little bit better. So here is the wire, and so that whole thing is the wire, right? Oh, J is equivalent to current over the cross-sectional area of that wire. We introduce it because it's important in the sense that with a point inside the wire, the Ampere loop doesn't cover the entire wire, it doesn't include the whole thing. So if the whole wire has a total current of I, right? Whatever is inside here is within this green area, it's only I divided by the total area multiplied by the area enclosed. So we call this thing the current density. So is that good enough? Yeah, in a sense, it's helping us to express that ratio. Yes. You're welcome. Thanks, Winnie. It didn't. I have to add that back in. Blah, 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 blah. So it's right here. That's my bad. Sorry. Okay then, same time next week then. See you.